Hello, everybody. It's time to continue our discussion about light as a wave. By this point, you've gone through the notes enough and you have watched the videos to be aware that light is nothing more than an electromagnetic wave. But what is a wave and what does it mean to be an electromagnetic wave? I have trouble picturing that in my brain. That's what this video is all about, is to understand what a wave is, how we can characterize a wave and say, hey, that wave is different than this wave over here. And then actually look at what a wave of light is, an electromagnetic wave. So I want to go ahead and start this by looking at what in the notes I call the anatomy of anatomy of a wave. But I'm going to take a slightly different approach, and we're going to deal with things one step at a time. So for the next several slides that I'll show over here, I am going to be showing the same example of a wave. Let's take a moment to appreciate what's going on with this wave. All right, so you have this nice oscillation, this nice periodic structure of high point, low point, high point, low point, high point, low point. We call the high points the crests. The low points we call the troughs. So the tippy top are the crests of the wave, the very bottoms are the troughs of the wave. Notice that this wave repeats itself, that it looks the same from this point to this point. So that distance where it repeats itself is what we call the wavelength. I'm going to come back to that in a second. But I just want to emphasize that so you can see that a wave is just this repetition, this periodic repetition of a pattern over and over and over and over and over again. In the case of this wave, it's showing you these red dots to show you if this was waves going through, say, on the surface of water, or a wave on a string, a bunch of particles, then the particles are just moving up and down, but the wave is traveling. Waves can move, and the wave is moving from left to right. So we can track that by following this crest of the wave. What is the physics definition of a wave? Well, a wave is a disturbance that propagates energy. So it's going to be some change, a disturbance that propagates energy, takes energy and moves it from one location in space to another location in space. So a wave is a form of radiation. It's taking energy and moving it from one place in space to another place in another place in space. What's unique about the wave, though, is that it is a regular oscillation. It is a vibration. It has this regular oscillation pattern going on. It repeats itself over and 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 over again. So this is just a depiction of a wave right here. How do we know that light is a wave? Well, as a wave, we can go out there and start studying waves, sound waves, waves on water, so surface waves, seismic waves, whatever kind of wave you want to, and we can start characterizing what properties it has, what characteristics. Waves can do this. A wave will bounce off an obstacle or reflect. As a wave goes from one medium to another medium, say air to water, it'll change directions, it'll refract. So we can catalog what all these wave properties are, and then we can look at light and go, hey, light, do you have these same properties as a wave? And you can check. One property after another. Yes, light does that. It does that wave property too. It has that wave property too. Has that wave property as well. It exhibits all the properties of a wave. And this is pretty much an argument of it looks like a duck, quacks like a duck. Well, it's a duck. So it has all the properties of a wave. It behaves like a wave. So we say that light is a wave. And it's this nice periodic oscillating entity. And since it has this nice controlled behavior, we can come up with some characteristics of a wave. We can define the anatomy of a wave. And we can connect all those ideas together. So we have the wavelength, the frequency, the amplitude, and the speed that the wave travels. And that's what I'm going to do. I'm going to successively walk through each one of these, what the wavelength is, what the frequency is, and I'm going to skip what the amplitude is because that's not super important to our discussion. You can get that from the notes. And then I'm going to connect the wavelength and the frequency to the speed. Okay, so what is the wavelength? The wavelength, which in astronomy and physics, we usually use the Greek lowercase letter lambda. So it's a lot easier than writing wavelength over and over and over and over again. Just write the letter lambda, and it's fun to write. So you'll see lots of lambdas flying around in this astronomy class. The wavelength is simply the distance between two successive wave crests. So the distance is marked right here from this wave crest to this wave crest. Notice that as the wave moves, that distance remains the same. The distance between the wave crests always remains the same. And that distance is what we call the wavelength. It really is, we could measure from trough to trough, we get the same answer. We could measure from, say, this height to the next point where it's that high. It's really the distance over which the wave repeats itself. So how far can you move along the wave before it starts repeating itself? So that's what we mean by wavelength. You can measure by crest to crest or trough to trough, or you can get clever and measure it by one point, follow the wave until it starts repeating itself again. And this is a physical distance. We measure the wavelength, it is a length. So we use our length units, meters, if we're using, say, the metric system, but you could use feet or inches if you wanted. They're just units of length, centimeters, millimeters, and if we're talking about light, or at least the light that the human eye usually sees, we're talking about wavelengths that are micrometer, micron, millionths of a meter, or nanometer wavelengths. So billions, hundreds of billions of a meter is the typical distance between the crests of visible light waves. Okay, so wavelength, just a physical distance. How long, what is the distance before a wave repeats itself? So frequency is just a count of how many wave crests are going to pass a certain point in a second. So if I had a wave that was going past me, and I was going to sit here and count the number of wave crests that were going by me, if I could see them, I'd be like, crest, 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 crest. And in 1 second, say I counted like 5 crests, it would have a frequency of 5 cycles every second. I could count 5 crests of a wave every second. So all frequency is you're just counting how many wave crests are passing you every second. How many wavelengths are passing you every second. I've tried to demonstrate that by, let's just put this line here. And frequency is how many wave crests will pass through this line every second. So I could go ahead and count 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. Okay, so less than 1 per second. It took me 4 seconds, and you can count as well. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. There's 4 seconds between wave crests, which means that I would see it would be 1/4 of a wave every second. So over 4 seconds, I would see wave crest to wave crest. 1 wave would pass me by. 1 segment of the wave would pass me by. So we'd say that in this case, this wave has a frequency of 0.25 hertz, 1/4 of a hertz, where a hertz, the unit we use for frequency, the SI unit we use for frequency, is just number of cycles per second. How many wave crests are passing me every second? And here we'll use the fractional amount. It takes 4 seconds for 1 wave crest to the next wave crest. So we would see 1 wave crest every quarter. So we'd get 1 cycle of the wave, 1/4 cycle of the wave every second. Not so bad. It's just how many wave crests per second. I want to give you another example of this though, and maybe teach you a little bit something about how your radio works, if people still listen to radio. So an example of frequency using a radio wave, which is electromagnetic radiation. Oh wait, radio waves are electromagnetic radiation. Radio waves are therefore light. And we can use this example of a radio wave, something that we're all a little bit familiar with, to demonstrate this concept of frequency. So our local national public radio station has the frequency, or it is the station 91.9. That's the number that you turn your dial to, or you push your buttons to make it read 91.9. If you get your radio reading that, then you're listening to the local NPR station, WUOT. 91.9 what though? So if you look at your radio, next time you get in your car, go ahead, whatever radio station you're on, look at the number, and then look what's next to it. And it'll say capital M, capital H, Z. Well, the HZ is hertz. We know that the capital M means mega, so 91.9 megahertz. So the radio wave, yes, that's a form of light that carries the information, whatever I'm listening to on NPR, that's carrying that information to me. That radio wave has a frequency of 91.9 megahertz. That's 91.9 times 10 to the 6th hertz. That's 91.9 million wave crests passing me every second. That's a lot of crests every second. I can't count that fast. 91.9 million wave crests passing by every second. If I tune my radio to receive that type of light, electromagnetic radiation, then I'm listening to NPR. We just put some technology in there that will then take the information that's contained on that wave to translate that to sound. And now you know the secret to radios. Now notice this is 91.9 megahertz, that's FM radio, which means frequency modulated. So how do they actually transmit information about sound, whatever you're listening to? Well, notice that you only have odd numbers available on your radio station to be like 91.7, 91.9, 92.1. That gives you a little bit of leeway. It gives you some space between the radio stations where you could wiggle the frequency around. You can modulate the frequency. So yes, 91.9 megahertz is the center, the main wavelength, but then you can modulate around that, add a little bit, subtract a little bit, change the wavelength of the wave a little bit, and in that changing of the wave, you can encode information that then your radio can translate to listening to Led Zeppelin. Kind of cool, right? Hopefully that brings this down and grounds this information just a little bit. Because now I want to put this all together. So the wavelength tells me the distance between the wave crests. The frequency tells me how many wave crests, how many numbers of wavelengths are passing by me every second. So wavelength is the distance between wave crests. Frequency is telling me how many distances, how many wavelengths are passing me every second. So the wavelength times the frequency would give me the total number of wavelengths, a set distance, time, and how many of those wavelengths are passing me, how that distance per second. So a distance per second, that's a speed. So if I take the wavelength and I multiply it by the frequency, I'm really calculating the distance that a wave travels every second. That's the wave speed. That's how fast this is moving. So the wavelength times the frequency, this is true for all waves, the wavelengths times the frequency will give you the speed of the wave speed. That's really cool. And now we can exploit that. Remember I said that doesn't matter what type of light I'm talking about? That all light travels at the speed of light? So that wave speed for all light is fixed to a certain value. The speed of light that we label with the letter C, and that equals 300 million meters per second, 3.0 times 10 to the 8th meters per second. And I know that that wave speed equals the frequency of the light times the wavelength of the light. So I can go ahead and I can write that into an equation. What is an equation other than just a very short way to say a long thing? And I can say, oh, the wave speed for light, the speed of light, is equal to the wavelength of light times the frequency of light. And now we have something pretty profound. So it doesn't matter what kind of light you're talking about, all light, radio light, the light that we see with our eyes, all travels at the same speed, the speed of light. So we get this equation where we know what this number is. So if we wanted to think about frequency and relate that to wavelength, we can see that these two things are really connected. And notice that the frequency equals the speed of light divided by the wavelength. You don't have to memorize these equations, but let's go ahead and start connecting some of the course concepts. The frequency equals the speed of light divided by the wavelength. As the wavelength becomes a bigger number, I divide by a bigger number, that means the frequency is going to be a smaller number. As the wavelength becomes a smaller number, divide by a smaller number, that means the frequency is going to become a bigger number. Oh, that's inversely proportional. So frequency is inversely proportional to the wavelength of light. Another way to think about this is if you want this to be the same number all the time, the speed of light, if this one gets bigger, to balance it out, I have to make this one smaller. If this one gets smaller, I have to make this one bigger so it balances out, so that always equals the speed of light. So frequency is inversely proportional to the wavelength of light. The wavelength is inversely proportional to the frequency. And all I did was a little bit of algebra here, using that C equals the wavelength times the frequency. So I could rearrange that. The wavelength equals the speed of light divided by the frequency, which is just telling me that the wavelength is inversely proportional to the frequency. As this number gets bigger, this number gets smaller. As this number gets smaller, this number gets bigger. Inversely proportional, and the change happens proportionally. This becomes 5 times smaller, then this becomes 5 times larger. This becomes 10 times larger, this becomes 10 times smaller. So frequency and wavelength are inversely proportional to one another. So let's compare two different waves of light to one another. So if one has double the frequency than the other one, then it also has half the wavelength of the other. If one wave has 5 times the frequency of another wave, then it also has 1/5 the wavelength of the other. If one wave has 1/10 the frequency of another wave, then it also has 10 times the wavelength of the other wave. And now we can start relating wavelengths and the frequencies. We can see how they balance out. We can understand that wavelength and frequency are the unique parts about this. They are what are determining what kind of light we're talking about. The only thing we haven't done yet is we've looked at waves, we've looked at the wavelength, we've looked at the frequency, we've looked at how they connect to give us the wave speed, but we still haven't answered the question, what kind of wave is light? It's an electromagnetic wave. Okay, fine. How do we define wavelength and frequency? What's going on with an electromagnetic wave? So let's take a look. This is our electromagnetic wave. Remember that electromagnetic means that you have an electric field part and a magnetic field part. The electric field is the red, the magnetic field is the blue. The electric field is labeled by an E. We label magnetic fields with the letter B in physics. Notice that it has this nice oscillation of stronger electric field, weaker electric field, an oscillation of the electric field. Perpendicular to that, we have an oscillation of the magnetic field. But they're just oscillations. Notice that it still has the same periodic nature. We just have two waves that are an electric field wave, and a magnetic field wave that are connected to one another. We still have this wavelength right here. We still have that wave speed. We can count the number of crests that are going by every second. So we have all those same parts of the wave. And notice that the wavelength and the frequency of the electric field part and the magnetic field part, the E part and the M part, they're the same. This wave travels at the speed of light. So we know we can now connect the wavelength, how the spacing between the crest of an electric field and the crest of the next electric field part. So do the same in the magnetic field part, same wavelength. And we can connect that using the speed of light to the frequency of that light. So it really is the wavelength and the frequency. I happen to have a wavelength bias. It's just the type of astronomy I do. So I've always worked with wavelength. So in this class, I'll stick to what I communicate best with, which is wavelength. So you all will probably have a wavelength bias as well. So let's go ahead and take our wavelength and figure out, oh, well, what are the possibilities? For light, we could take that wavelength and we could stretch it out, make it bigger and bigger and bigger and bigger and bigger until it is essentially infinite in length. We can also make it really small, down to almost zero, approaching zero wavelength. So we can stretch it out and squish this thing down. We just have to change the frequency accordingly so that the two multiplied together always equal the speed of light. Which means that we have an infinite possibility on the number of wavelengths. So perhaps what we want to do to distinguish the different types of electromagnetic waves, the different types of light, maybe the best way to communicate the differences of the types of light is by their wavelengths. This type of light has this range of wavelengths, visible light, say 350 to about 800 nanometers wavelengths. That's visible light, that's what humans see. Radio wave light has wavelengths of meters to tens of meters to kilometers. So we can distinguish the different types of light by their wavelengths. Or if you want to do it by frequency, you could do it equivalently by frequency, since those two are related to one another. All right, so do we answer anything? What is light? Well, light is this little tiny package of a coupled together oscillating electric field and an oscillating magnetic field, which the two are perpendicular at right angles to one another, hurtling through space at the speed of light, and that is what light is. This little tiny package, this oscillation of an electric field and a magnetic field, hurtling through space at the speed of light can enter your eye, interact with your retina, your rods and cones, send a signal to your brain, and all of a sudden you can see what's going on around you. You can interact with the world around you. And that's how our eyes are going to work. We're going to have specialized receptors. We're going to have molecules that are receptive to different wavelengths of light that can detect electromagnetic radiation. And then our brain pieces that together into the world that we experience. All right, I will go ahead and stop there. Hopefully you now understand wavelength, frequency, and the speed of light.